Alright, so we before I do more examples, let me get to another main idea for this topic. And that would be the following main idea. What if you could say that, let me see, whoa, that was too fast, what ifs. What if you could say that that the n plus 1 term on a sequence divided by the n term tends to be something like a common ratio r. What exactly does that mean? We're going to take 2 minutes to explore exactly this statement. This statement, for example, would tell you that a2 over a1, that's when n is equal to 1, is equal to some constant r. I don't know, you could pick whatever you want. I'll just leave it as r. Alright, that would tell you that a2 over a1 is equal to r. That in turn implies that a2 is probably equal to r times a1. Or approximate, whatever you like. Right? All I did is multiply both sides by a1. But wait, there's more. What about a3 divided by a2? According to this recipe, every single time I take consecutive terms and I take the ratio like that, I get the same number r. So a3 divided by a2 would be still r. That would tell me that a3 is equal to r times a2. You say, well, this is boring already. But wait, there's more. This would tell you that a2 I could substitute from the line above and put it in here. I can exchange that for ra1, leading me to believe that this must be r times a1. Or said differently, leading me to believe that this is r squared times a1. Or approximate, whatever you like. So a3 is equal to r2 times a1. But wait, there's more. What would this thing tell me about a4 divided by a3? It would say, well, it's approximately equal to r. That's what this recipe says. It says for every consecutive term, you take the next one minus the previous one, you get the same ratio r. This would tell me that a4 is equal to r times a3. But wait, a3 was equal to that. So I can exchange it for that, and I can say a4 is equal to r times r squared times a1. Wait a minute. This means that a4 is equal to r to the third times a1. Yes or no? And we can go on. We could go do this all day long. But wait, let's not think like an insect. Let's think like a human being. Eventually you'd get to the pattern here and say, well, what is a100 equal to approximately? Well, it would probably be r to the 99th power times a1, more or less, right? In fact, you could always say this, a to any power is equal to r, and of course you're off by a constant, but so what? An will approximately be a constant times r to the nth power. That right there is golden. You know what this does is this reveals that anytime you have consecutive terms, the ratio is equal to r. It reveals explicitly, oh, that must be a geometric series. Of course, you knew that if you know anything about recursive sequencing and you took a decent pre-calc class. But nevertheless, we see it explicitly developed how this fact right here identifies A and the sequence as a very close relative of a geometric sequence. That right there is a key. Anytime your ratios like this gives your R, you've got fairy blood here. You've got a geometric series sequence. Alright, so let's make that formally then. So then, based on that little discussion, we make the following claims. If that limit is equal to r, then of course your sequence is like a geometric. It's fairy-like. And then of course, under some reasonable conditions, then you can slap sums on both these sides. So the original series would be similar to the geometric version of it, where r is the limit that you got from the ratio. Okay. All right. Talk is cheap. Let's do it. Formally, you need absolute values. Look at this ratio. If it's equal to r, and of course r is not equal to 1. We talked about this on the last video. Then of course the series behaves like a geometric series. Those are your tests. Let's just actually do an example. So we're going to try to figure both of these things out and see how it goes. Let's go with yellow. Yellow mellow. Alright, so I'm going to take the n plus 1 term. That would be, I need a n plus 1 divided by a n. So that means wherever I see n, I plug in n plus 1. So it'll be n plus 1 divided by pi to the n plus 1. That's my an, and I need to divide that by just a plain one with n's. I need to simplify this just a bit. Maybe I'd say this is n plus 1 divided by pi times pi to the n times pi to the n divided by n. Maybe I simplify this more. This goes, that goes. And so I've got myself, let's see, what do we have now? This simplifies to n plus 1 divided by pi n. And I can further simplify that. That becomes 1 over pi plus 1 over pi n. And now I've got to take the limit. The limit for all this is n runs towards infinity. Of course, there's no n here, so that stays. N goes towards infinity, creating that to be, making that go to 0. This limit is clearly 1 over pi. Winner, winner, chicken dinner. I got myself my ratio r. So this tells you that r is not 1. This is not equal to 1. So this tells me that this one behaves a lot like a geometric series. It behaves like 1 over pi to the n. Yay. Now it's all over. We just have to maybe make it formal, and we're good to go. Clearly, oh, by the way, does this converge or diverge? Because this is less than 1, we already talked about this in the previous video, this would converge, and then we'll be done. Alright. Having checked these two things off tells you that these two behave the same, behaves like a geometric series. The easiest, most enjoyable series in the entire world, the geometric series, converges just by looking at it. Your r is less than 1, and you're done. Alright, come back for another example. For that example, we'll see you guys here next time.